Okay, so in the previous lecture, we have started to construct a relativistic local quantum theory, and we have shown that such a theory is in fact a quantum field theory, since the basis of the local observables was obtained using scalar fields, which were integral superposition of the gradation and annihilation operator in the form which looks like this. And we have shown that provided these gradation and annihilation operators commute the invariant delta function, of course, the annihilation operators as well the gradation operators commute to 0, then this set of fields, this field, scalar field, is causal in the sense that if we calculate commutation relations in two spatially separated points, then we obtain 0 for x minus y squared smaller than 0. From the very existence of this causal field on our Hilbert space, we were therefore able to determine the statistics of the particles. The particles were bosons. Of course, our input to this construction was just our Fock space, which was generated by some vacuum and a set of gradation and annihilation operators. And the requirements which this field should fulfill, namely the requirements of locality and causality and relativistic invariance in the sense that the field is scalar. That means we get such a transformation property of our field. Of course, two natural questions appear in context of this construction. The first one was, what about the anti-commutation relations between the gradation and annihilation operators? What about fermions, which were spinless? We have already touched this, this question when we discussed the spin statistic theorem, and we will discuss this more in more detail later. So whenever we have anti-commutation relations between the gradation and annihilation operators, then there doesn't exist any other fields which would be causal. Namely, we can ask whether there is some other representation of the Lorentz group can be used to construct causal fields. The answer is no. These anti-commutation relations are in contradiction with the basic principles like relativistic invariance, locality, and causality. So in this case, causal fields do not exist. And the second question is, even if we use commutation relations, whether it is possible to construct other fields which were causal and which would transform under other representation of the Lorentz group. Here the answer, so if there exist other representations compatible with causality or bosons. And here the answer is yes, there exist. We will see in the general discussion, which we will do later, that there exist, in fact, infinite number of other compatible representations under which causal field associated with bosons can transform. And for instance, at this point, at this step, we can show, for instance, that any derivative of our original scalar field, phi x, does the job. So any such field can be associated with spinless bosons. Okay, we have shown a lot of properties of our scalar field. And we would like also to find how the scalar field, pseudo-scalar field, or whatever, can transform under discrete symmetries. We have advertised that the transformation properties with respect to discrete symmetries and the requirement of causality can give further constraints for our scalar field and give further constraints even for the transformation properties of our one-particle states. So what we know about discrete symmetries? We know that for the annihilation or creation operator transform under such a discrete symmetry in the analogical way as one-particle states. So in this case, it is just the phase, parity phase, and creation operator. With Hermitian conjugation, we obtain a similar relation, complex conjugated phase. And now we can try to calculate the transformation of our scalar field. So using our general form in terms of creation and annihilation operator, and using these relations, we simply obtain, this is the transformation of the annihilation operator, and this is the transformation of the creation operator. Of course, forget about the tilde operation, which reverses the sign of the spatial components of the momentum. So what we get is such a relation, and we see that we obtain some new fields. Let us denote it phi with subscript p, and this new field is again a linear combination of creation and annihilation operators, but now with some up to now undetermined phase eta p, which goes along with this creation and annihilation operators. And now we can remember what we have said about the possibility to add to our theory any other field with different phases at the creation and annihilation operators. You remember that this would not be possible since it would lead to violation of causality. Simply this new field, phi p, would not commute with our original field phi at special separated instance. This would not be 0 when x squared is space-like. So the only possibility how to avoid this situation, provided we would like to have a parity represented on our Hilbert space, and we have it because we have action of this parity operator on one-particle and multi-particle state, is that these phases obey the condition that, eta p complex conjugated is the same as eta p, since in such a case we can put this phase in front, so we obtain, say, eta p times such a superposition of creation and annihilation operators. This is fine, since the phases of the creation and annihilation operators are the same as in our original expression. The relative phases are the same, and therefore the causality is preserved. So the only possibility is that this pure phase is just plus minus 1. Let us rewrite this final formula in additional form. So let us make a substitution simply from the integration variable k. Let us go to integration variable minus k. That means from k tilde we will go to k. Of course, our measure, d tilde k, which is ordinary three-dimensional measure over 2 pi third to relativistic energy ek is invariant with respect to such a change of the sign of the integration variable. And this scalar product k times x will be expressed in the new variables as k tilde times x, which is just k0 x0 plus k times x scalar product. But this is nothing else but k times x tilde, because again, this x tilde defined as x0 minus s, the sign as this term is changed. Therefore, using this substitution, we can write this in the form d tilde k times a k e to the minus e k times x tilde plus a cross k e plus k times x tilde. And if we compare this with the original expression of our field phi, we get that this is just phi in the point x tilde times this phase p. Therefore, we see that causality constrained the up to now free parameter eta, the phase which determines the action of the parity to one particle states to be plus minus 1, and the corresponding transformation rule in the end is p x p cross is just eta p, that is plus minus 1, times phi at x tilde. And this right-hand side is nothing else but the transformation property either of scalar for eta plus or pseudoscalar. We can do similar exercise with t inversion, but now we have to be a little bit more careful since t is anti-unitary operator, and we can use our relation for transformation of correlation operator and the annihilation operator. To write this as linear superposition of eta t cross times a k tilde, but now we have to commute in this original expression the t operator through this exponential. And since the operator is antilinear, we obtain complex conjugated exponential. So we get here e to plus I k times x, plus similarly for the annihilation creation operator, eta t cross k tilde e, and again the change of the sign in the exponential is I k times x. And again, we can argue, as in previous case, that the only possibility to preserve causality is that this eta t star is eta t, and therefore plus minus 1. And again, we can do such a substitution in our integral and obtain. So we can put this phase in front. And we have here, I will write it in some suggestive form, minus I k times minus x tilde. The trick is the same. K becomes k tilde, and using this relation, like this, but we have changed the sign here. And similarly, a cross k times e to plus I k times minus x tilde. And comparing this with the original expression for our phi, we obtain that the t transformation of our field is just this phase times the original field, but now in minus x tilde. Note that in both these relations either for parity or T inversion. This x tilde is just the parity transformation of the for vector x, and in this case the minus x tilde is nothing else but the T inversion of the original vector x. So we have seen that the requirements of causality give us severe constraints on the transformation properties of our fields with respect to discrete symmetry, and also it determines up to a sign the phase which enters the transformation property of one particle states under parity, and the same constraint we obtained also for the T phase, but we know that this T phase is not physical, can be removed by rephasing, creation or annihilation operators, or one particle states. Okay, so up to now we did the construction of local relativistic quantum theory in the bottom-up approach, in the sense that we have a lot of inputs which were used in order to construct the field operator on our Hilbert space. Namely, we needed the Fock space, we needed the transformation properties of the fields, we needed the requirement of causality. This results in the construction of causal field, which in the end obeys such a commutation relations. Let us denote this right-hand side as I delta x minus y, which is known sometimes as Pauli-Jordan function, commutator function. We will do such a construction later for general spin, and we will see that these requirements will give us again constraints both on the statistic of the particles, both on the possible representations of the Lorentz group under which the causal field transform, and also on the transformation properties with respect to discrete symmetries. But let us now start with this relation, and let us ask whether we could obtain such fields using another principles. Well, it is clear that if we would like to construct the fields which commute in this way, we can use a lot of other properties of our field. For instance, we know that our field obey the Klein-Gordon equation. This was the result of our construction. Therefore, this commutator, again, as a function of x, obey this Klein-Gordon equation. So how can we reconstruct this Pauli-Jordan commutator function? Simply solving this Klein-Gordon equation as a function of x, and for this solution we need the initial conditions. And the useful initial conditions for such a task are the condition for x0 equals to y0. That means the initial conditions for such a function, for this Pauli-Jordan function, should be given by the commutation relations of the fields at equal times. Of course, this is the second order differential equation, so we need not only the commutation relations at x0 equal to y0, but also we need the time derivative of this commutator. Therefore, we need derivative with respect to x0 of this commutator at x0 equals to y0. And once we know this initial condition for our Klein-Gordon equation for this commutator function, we can solve it and obtain uniquely the solution as the Pauli-Jordan function. This is the motivation for so-called canonical quantization, which instead of starting with Fock space, starts rather with the algebra of the fields, namely with the commutation relations at equal times, and with the requirement that the field satisfies the Klein-Gordon equation. Okay, so let us now try to calculate these initial conditions and find the so-called canonical commutation relations for our scalar field. And then we will try to use these canonical commutation relations to reconstruct completely not only the fields, but also the Fock space, which is associated with such a fields. And we will see that then, of course, the causality is automatic, and the relativistic invariants would need to implement again the requirement that our field transforms as a scalar field. But the bonus of this approach will be that the former input, namely the Fock space, will appear almost automatically in such approach, and also that the causality will be automatic. So what we need is to calculate this commutation relations. So we know what is it? Phi x, phi y, for x0, zero's component of x is the same as 0 component of y. So we have to express this in terms of creation annihilation operators and calculate the corresponding commutators, but we know what is the result. The result is given here, where this delta plus I delta plus function is given as integral over invariant measure of e to minus I k times x minus y. This is for this term, and similarly minus dk tilde e to plus I k x minus y. This is for this second term. And in this expression, we should put x0 equal to y0. And therefore, we obtain just d tilde k e to, here the 0 component of k of x minus y is 0, and therefore from the 4-vector scale product, we obtained only the 3-vector scale product I k times x minus y. And in the second term, we obtain similarly e to minus k times x minus y. And using the trick we already have used in the previous calculations, namely changing the integration variable from k to minus k, we see that the second term is the same as the first term, and these two terms cancels, and the result is 0. So this is one of the canonical commutation relations. And let us now calculate the second one. Therefore, let us calculate the time derivative with respect to x0. So what we get? Simply deriving this term with respect to x0 will give us d tilde k times minus k0, and k0 it is nothing else but the relativistic energy, since we integrate over the mass shell. So it is minus I and energy times this exponential, and in this exponential we put x0 is I0, so here we get just this exponential I k times x minus y. And in the second term, we obtain minus, and the derivative give plus I k0, so we obtain the same sign times e to minus e k x minus y. And again, here we change the integration variable. And since this relativistic energy is even with respect to such a change, we obtain in the end minus twice I d tilde k times e to e k times x minus y. But now we can remember what this delta k is. d tilde k is. And what we give here is therefore cancellation of this with this, and in the end this 2 with this 2, we obtain minus integral d3k times e k scale product over 3, and this is nothing else but the integral representation of delta function. So our result is minus I times 3-dimensional delta function of x minus y. So to conclude, our canonical commutation relations, if we denote the time derivative of our field phi x as px, we will later see that this px plays a role of generalized momentum, which is associated with our field. We obtain the following equal time commutation relations, which can serve as initial condition for our Cauchy problem of Klein-Gordon equation for the commutator, namely phi x y in the same times 0 and phi x I y, pi is the time derivative, up to a sign is just plus I, again at x0 equals to y0, delta 3 x minus y. And it is an easy exercise to show again that if we calculate such a commutator equal times, we obtain 0. So this is the set of canonical commutation relations which uniquely define the commutator of the fields phi, provided this field satisfy the Klein-Gordon equation. So let us try to use this plus the Klein-Gordon equation for the field phi to obtain more information about our system. So let us forget completely on the Hilbert space. We have only algebra of the fields and the Klein-Gordon equation. The algebra of the fields is expressed in terms of this equal time commutation relations. And let us show that these two ingredients allows us to almost completely reconstruct our Hilbert space. We will try to find the Hilbert space as the space which carries the representation of the algebra, which is determined by just these ingredients. So what we need is to solve this operator equation, this Klein-Gordon equation. And the way how to do is simple. Since it is differential equation which is linear, we can use Fourier transform of the field phi x and rewrite such a partial differential equation as an algebraic equation for the Fourier transform. So let us define fx as integral d4, this is some conventional factor, to pi to the 4th power, times some function, operator in fact, depending on x, times e to the minus I k time x. So this phi tilde is in fact the Fourier transform of our field. If we insert this to the Klein-Gordon equation, we obtain simply algebraic relation for this phi tilde, and this is nothing else but minus k squared plus m squared times this phi tilde k, and this should be 0. Okay, what does it mean? This means that whenever this is non-zero, the phi tilde should be 0. Therefore, the phi tilde should be non-zero only on the mass shell. Therefore, only for those case, or for vector case, which obey the constraint that k squared is m squared. So let us conventionally write this as 2 pi, this is again some normalization, times some ak, some operator ak, which depends on k, times delta of k squared minus m squared. This is the most general solution of this relation. Phi tilde k is 0 whenever k is on mass shell, is not on mass shell, and on mass shell the dependence of this fk is hidden in this operator ak. So let us insert this, and we obtain the general solution of our Klein-Gordon equation in the form d for k over 2 pi to the third power times this ak times delta k squared minus m squared times e to the minus e k times x. But this delta function can be understood as a delta function in the variable k0, and as such it can be rewritten as a sum over delta functions corresponding to the solution of this k squared minus m squared constraint. Therefore, the k0 should be here either plus or minus the relativistic energy. And we can rewrite this delta function as simply 1 over derivative of the function inside the original delta function, which is twice k0, and k0 plus minus ik in absolute value times delta k0 minus k plus second root of this constraint to k, again in absolute value, so with plus sign, times delta k0 plus e k. So if we insert this in our expression for the field, we obtain two terms, and for convenience we will write this as a function of k0 and k, and the first term will give us, in fact, the if we integrate this with respect to k0, we simply substitute for k0 in the first term plus ak, in the second term minus ak. So we obtain here the integration over spatial components of our 3 vector k, 4 vector k, and in the first term we obtain just a k, k, and from the second, so minus e k times x0 plus I k times x, and the second term simply a minus k, k times e2 plus e k x0 plus I k times x. Again, it is useful to make a substitution in the second integral, k to minus k. And what we obtain is just, remember that this is the expression for our invariant measure, d tilde k, times two terms, a k times e to minus I k times x, plus second term, a, here k comes to minus k, so here we obtain a minus k times e, and since we change here the sign, we can rewrite this exponential as plus I k times x, where we tacitly, of course, assume that this k has the components k and k. This is our final expression for the general form of the solution of the Klein-Gordon equation in terms of these undetermined coefficients, ak and a minus k. This was what was free in this general solution of our Klein-Gordon equation. And provided we suppose that our field is Hermitian, then we easily see that this a minus k should be this ak Hermitian conjugation. So what we get is something which resembles our previous construction. Simply here is some operator coefficient k minus I k times x plus a cross k times e I k times x. But what we don't know yet is how these operators ak and a cross k commute. So what is, for instance, ak a cross k primed? And here is the point where our canonical commutation relations comes into the game. Simply we will show that these canonical commutation relations are restrictive enough to show that these commutators are, as before, just the canonical commutation relations for the creation and annihilation operators for spinless bosons. So how to see this? We see that our field is a linear superposition of this. I will call them creation and annihilation operators, since we will see that the commutation relations will be correct. So it is a linear combination of these creation and annihilation operators, and we would like to express these creation and annihilation operators in terms of phi x and possibly the pi x. So let us remind you that this pi x was time derivative of phi, and therefore it can be also rewritten as a linear superposition of creation and annihilation operators. Now as minus I k, this time derivative of this exponential, times k a minus I k times x, and in this case plus I k times cross k times e plus I k times x. And in order to express the creation and annihilation operators in terms of phi and pi, let us calculate, for instance, such an integral. Here q is some parameter, 3 vector, times phi x. Okay, so what we get? We get two terms, one term coming from this one and the second term coming from this one. And we see that the only dependence of this phi x on the 3 vector x is just e2 plus I k times x from the first term and e to the minus I k times x from the second term. And integrating d3x e to the minus I q times x with e2 plus minus I k times x simply gives 2 pi to the third power times 3-dimensional delta function of either q minus or plus k. So if we insert this in this expression, we obtain integral d3k times e to minus I k0, that means e k x0 times 2 pi to the third power times delta of q plus minus k times a k, and similarly from the second term plus e2 plus I a k times x0 times 2 pi to the third power delta 3 of q plus k times a cross k. And taking the derivative, the integration with respect to delta function is trivial. We simply substitute for k q's minus q. So in the end, we obtain e to the minus e q times x0 I remind you the form of our measure. It is here. So 2 pi's are, we can therefore put in front, sorry. And here we get just a q plus e2 plus I q. Know that eq is even function of the free momentum times a cross minus q, in the 4-vector notation, q tilde. So this is the 3-dimensional Fourier transform of our field. And completely similarly, we get also the Fourier transform pi x, which is the time derivative of the origin of I. And here we obtain just minus I over 2 q times e to minus e q times x0 minus cross q tilde e to plus I e q times x0. And from these two equations, we can simply express AQ simply as e to I EQ times x0. We simply multiply this by relativistic energy EQ and this by imaginary unit, and add these two equations, and in the end we obtain the following expression. So this is the expression for the annihilation operator, and similarly for the creation operator we can either again use these two equations with Q, which is here with reversed spatial coordinates, interchange with Q tilde, or we can just make a Hermitian conjugation of this equation, and we obtain a cross Q as again e to the minus e q times x0 d3x q times x minus I px times e2 plus I q times x. Well, this is our expression for creation and annihilation operator in terms of the field phi and in terms of its conjugated momentum pi x. And now we can simply take this and put it in the commutation relations and calculate the commutation relations for A's, A crosses, and the mixed A and A cross. Let me make a side remark here. Notice that the left-hand side of these equations is not dependent on x0, while on the right-hand side we obtain something which had both explicit dependence here and also dependence implicit in this phi and pi. What is the reason for this independence? The reason is that in fact we can show that the right-hand side of these expressions can be also written in terms of the zero, of the integral of zero components of some, of some conserved current which is associated to the Klein-Gordon equation. Let us remind you that if we have two solutions of Klein-Gordon equation, phi 1 and phi 2, we can form a conserved current from them. And such a conserved current, which obeys such a conservation relation, give rise to a conserved charge, which is the zero, which is the integral of the zero component of this current. And this is time independent. This is integral of motion. And What we know, of course, is that e to, say, plus minus I times e k x0 minus I k times x is a solution of Klein-Gordon equation. And also our phi is a solution of the Klein-Gordon equation. And our pi is a time derivative of this solution of Klein-Gordon equation. So it is an easy exercise, which you probably do yourself or seminar, to show this, that these creation annihilation operators, these right-hand sides, can be expressed as just I integral of d3x over e I q times x now 4 vectors times d0 both sides phi x. And since this is a solution of Klein-Gordon equation, and this is a solution of Klein-Gordon equation, this is x0 independent. Okay, so it is only easy algebra now to take these right-hand sides and put them to the commutation relations. For instance, let us do it for AK, A cross K. So what it obtain here, according to our expressions, it is double integral over, say, dx, and for a cross, let us use the variable dy times e, and let us use the fact that in fact these expressions are x0 independent. So let us take the time in the right hand side of this one and this one the same. Therefore, these exponentials now cancel each other, and we obtain only exponential of the form minus I, say, k times x plus I q, sorry, k primed times y. And what we obtain here is just the commutator of these two brackets, one with q and the other with k and the other with k primed. So we obtain here just k phi x plus I px and k phi y minus I pi y. And since we have chosen the time component of x and y the same, this commutator is taken at the same times. Okay, now we can calculate these commutators using the canonical commutation relations at equal times. So we obtain here d3x, d3y, e to minus I k times x plus I k primed y. And what we get here is just commutator of this term and this term, which is 0, this term and this term, which is non-zero, and which is just, sorry, ek times delta function. Remember the commutators here. So this minus I with I times delta function of x minus y. And the second term here is just this by this. Here we obtain just ek primed time again delta function. This one sign change since the commutator is pi phi in comparison with the commutator of phi pi in this order. So we obtain here again delta 3 x, and this is the complete expression. And now let us first integrate over x. This gives us that y is x in both cases, and what remains is b3x times ek plus ek primed times e2 minus I, say, x times k minus k primed. And again, we obtain here the integral representation of delta function with respect to this variable. And therefore, the k and k primed could be taken the same. And as a result, we obtain 2 pi to the third times delta function of k minus k primed times 2 ek. And this is nothing else but our invariant delta function k minus k primed. So we have shown that such a commutation relation holds as a consequence of the canonical commutation relation between phi's and pi's. And similarly, we can show that also ak prime is 0. Simply it differs in the sign here. Therefore, in the sign here, and instead of adding these two, we obtain the subtraction of these two terms, which is 0. And for instance, by Hermitian conjugation, we obtain that also the creation operators. So what we get from our original requirements, that means the fact that our field respects the Klein-Gordon equation and that we have canonical equal time commutation relations, we simply obtained the algebra of creation and annihilation operators. And what about now the Hilbert space on which this operator algebra is represented? Can we reconstruct it uniquely? The answer is yes, provided we suppose that in such a Hilbert space exists a state called vacuum, which is annihilated by all the annihilation operators. Provided this is true, we can simply construct such a Hilbert space as a space based on vectors p1 to pn, which is just a cross p1, a cross p2, and so on, a cross pn on the vacuum. And every action of the creation and annihilation operators, and therefore also the action of the fields on such a space, on such a basis, is given purely using this algebra. For instance, if we would like to see what happens when we use this, it is simply a cross p, a cross p1, and so on, a cross pn on the vacuum, and in our notation it is just p, p1, and pn. Or what about action of a p, p1, pn? It's simply a p on a cross p1, a cross pn vacuum, and now we can try to commute this AP operator through this creation operators, let it act on the vacuum according to this relation. And each such a commutation gives us one invariant delta function. Therefore, we can write it as AP commutator A cross P1, AP2, and so on the vacuum, plus the term with additional, with reversed order of the operators, A cross P1, AP2, AP, A cross P2, and so on. And this we know from our algebra, this is our invariant delta function. So what we get is just delta P1 minus P times A2 cross P2 cross Pn in the vacuum, and doing this successively, we obtain the usual action of the annihilation operator. Simply sum j goes from 1 to n, delta tilde j minus p, and here is set of operators I a cross p1 up to a cross pj minus 1, a cross pj up to pn, a cross pn on the vacuum, and the last term would be the situation where this AP acts on the vacuum, but we know that the vacuum is annihilated by the annihilation operator, so this is complete action. So we see that really on such a vector space, which is generated by these vectors p1 to pn, the creation and annihilation operators acts in the usual way as we expect. And what about the scale product on this Hilbert space? The scale product is again completely determined by this algebra and by the postulate that the operators, annihilation operators, Hermitian conjugated, are just the creation operators. For instance, if we are interested in the scale product of, say, P1 and P2, it is just according to our rule, vacuum A P1, A cross 2, but we can rewrite this as the commutator plus the reversed order, but this P1, when acting on vacuum, doesn't contribute, and we obtain here just invariant delta function times the norm squared of the vacuum state. If we add to our postulates also normalization of this vacuum state, we obtained just the usual normalization of one-particle states. So, what we have seen? We have seen that the Klein-Gordon equation plus canonical commutation relations plus existence of the vacuum allows us completely reconstruct of our Fock space, including the statistics of the particles. But what we haven't yet is the representation of the Poincaré group on our Hilbert space, since up to now we have reconstructed only part of our complete local scale field theory. So what is missing is the representation of Poincaré group. And this can be obtained postulating the action of our representation of the Poincaré group on the fields, simply postulating that this is just the scalar field, and with respect to translations, this, and also with respect to discrete symmetries, we postulate this, and with respect to the time inversion, we postulate this. Well, this is our postulate how these operators representing our Poincaré group acts on the fields, and what we need is the action on the states, which can be obtained by the action on the creation and annihilation operators. But we know how to express creation and annihilation operators in terms of fields. So we can make a reversion of what we did in the previous bottom-up construction, and from these relations to deduce what is the action of these operators U and P and T on creation and annihilation operators. Well, this is in fact a rather easy exercise. Simply using our expression for the field in terms of creation and annihilation operators, and inserting this, for instance, to the first equation, and simply comparing both sides of this equation using the fact that these exponentials are linearly independent, so the coefficient and these exponentials on both sides should be equal, and you simply obtain what we expect, namely this relation, for instance. Sorry. And so on. So I leave it, these manipulations, as an easy exercise for you to show that these transformation properties of the field are equivalent to the corresponding transformation properties of the creation and annihilation operators we have obtained before by the bottom-up construction. Let me make one remark. For our reconstruction of the Hilbert space, it was crucial that we had this vacuum state. Such a representation in the Hilbert space of which such a vacuum state exists are called Fock representation of the canonical commutation relations. But there could exist also representations which are not of this type. Simply, if we have some Fock representation, therefore we have creation and annihilation operator and some Fock vacuum, we can construct in this space simply new operators, bk, which is just this ak, for instance, minus some constant c, and b cross k is the original ak minus c for complex conjugated. This c is c number, therefore, in fact, we should write c times identity operator here. Of course, this b and b cross obey the same commutation relations in this addition to them commute with all other operators. So again, b, and b cross are 0, and b cross are invariant delta function. But if we would like to find some vacuum state with respect to this annihilation operators pk's, let us denote it in such a way, we would find that such an operator doesn't exist inside this Fock space. Simply because the only possible algebraically consistent vector which should have this property would be of infinite norm with respect to scale product on this Fock space. And therefore, such a representation with these b's is not a Fock representation. It has not vacuum state. On the other hand, if we have two representations of the same canonical commutation relations, say A cross and some vacuum on one Fock space and some second Fock space where it is realized by some primed operators and some primed vacuum, then these representations are unitary equivalent. That means that we simply have unitary transformation from this basis to the prime basis, simply defining this as defining defining the action of such a unitary operator on acting on this F space as the corresponding basic vector in the second representation. That U is operator which maps from F to F primed, and the action of this operator in our basis is just given by this. So any Fock representation, any two Fock representation are unitary equivalent, but there exist non-Fock representations, and these non-Fock representations are not unitary equivalent simply because the vacuum of the non-Fock representation doesn't exist, so it cannot be by unitary representation acting inside such a Hilbert space to this normalized Fock vacuum corresponding to an original construction. Okay, so we have just in time, so I will stop here.